Great. I think we can get started. So, hi everyone. Today we have Noah who will be telling us about coins, partitions, and generating functions.
All right. Yeah, it's a pleasure to present. All right, let's go through. As the name suggests, we're going to talk first about a certain problem with making change with coins. And we're going to solve that problem using a technique known as generating functions. And our technique will lead us into a broader discussion of a mathematical abstraction in combinatorics known as partitions. So first, let's kind of define our problem. So say you have K cents, and this could be, like 10 cents or 100 cents. And we're interested in how many different ways we can express these K cents as a combination of coins. And, in the most relatable sense, this is coins like pennies, nickels, dimes, and quarters. But obviously, perhaps not obviously, you can abstract this problem and think about coins of all kinds of values. For example, you could have a 3-cent coin, like a 6-cent coin. And the problem changes based on those kinds of different coins that you have available. Some related questions that you might see if you look this problem up are a variant. So, for example, you might be interested in the minimum number of coins necessary to express K cents. And this is, if you're interested in the terms of art, this is a special case of the integer knapsack problem. You could also think about, like, a further question is, what series of coins minimizes the average number of necessary coins, which is kind of a complicated question. But the best way to put it is what kinds of coin denominations will make change making the easiest. And it turns out that our own system, it works well, but it might not be the best. I was reading an article by Shallot that said that what this country needs is an 18-cent piece. And they go through a bunch of the mathematics to show that apparently if we have an 18-cent coin, it would make change making a lot easier. Stuff to consider. But in our case, we're worried mostly about this combinatorial problem of how many ways we can express K cents. Here's just an example. If we have 11 cents and we have our normal sense of coinage, then there are 4 ways we can express 11 cents, right? We could do 11 pennies, we could do 1 nickel and 6 pennies, we could do 2 nickels and 1 penny, or we could do 1 dime and 1 penny. And obviously that last one is the fewest number of coins because it's only 2 coins. Now, it might seem like this problem is pretty easy to find the fewest number of coins. If you use this kind of greedy method approach where you choose the biggest coin that fits under K, and then you choose the next biggest coin that fits under K and whatnot. But it turns out that doesn't always work. And I challenge you to think of a counterexample and a certain kind of coinage where this wouldn't work. Because it's kind of a fun problem. Here's just visualizing different kinds of coinage and the number of ways we can express K cents in terms of those coinages. So, for example, if we only had pennies at our disposal, there's only one way to describe any number of cents, right? And that is to have K pennies. But if we introduce nickels as well as pennies, then it gets more complicated, right? For example, if we have 5 cents, then we can express it as 1 nickel or 5 pennies. And then if we add dimes into the mixture, again, things get more complicated because there become more combinations. So in general, the more kinds of coins you add to the problem, the more complex the problem is going to become. Here's just a mathematical formulation of it. It's not totally useful, but for our purposes. But if you see this problem in other areas, you can think about it like you have 2 vectors, one vector that describes all the different kinds of coins and their values, and then another vector that describes the number of coins of each type that you have. And then essentially what you're doing is trying to find how many distinct X you can multiply with W with a dot product such that you yield K. And here's just a physical example, not a physical, but an example you can see. So if you have the normal sense of coinage with pennies, nickels, dimes, and quarters, then you can take 1 penny, you can take 2 dimes, you can take 0 nickels, and you can take 1 quarter. And if you take the dot product of these 2 vectors, which is essentially this operation, you just add the corresponding terms, then you get 46 cents. So this is all just kind of priming you for understanding this problem well. Now, if you go through different solutions to this problem, you can, the most immediate solution you might think of is some kind of recursion, where you start with K cents and then you subtract each kind of coin denomination. So let's say you start with 40 cents and you subtract 1 cent, you subtract 5 cents, you subtract 10 cents, and you subtract 25 cents in like separate kind of tree pathways. And then you treat each subproblem with recursion again. So what you do is essentially you build up this tree that breaks your problem down into smaller subproblems. And then of course you'll have some kind of base case. So like if when you subtract the coin, it becomes 0, then you know that that was not a valid method. And so essentially, if you build out this entire tree, then you could figure out which is the shortest. You could figure out how many valid branches there are. But this is very, very time consuming. If you think about this in terms of big O notation, it's O of m to the n, where m is the number of coin types. And that's because m is the number of branches you're creating in the tree at every step. And an obvious solution, if you're familiar with algorithms, is to introduce some kind of dynamic programming, some kind of record keeping, where you build up your solutions from 0 to n, or you do recursion, this kind of recursion technique, except you make sure you memorize when you've done something before. So the issue with this recursion is that you repeat a lot of the subproblems again and again, but with dynamic programming, you can kind of cut that out. You could say, okay, wait, I'm trying to calculate the tree for 9 cents, but I've already calculated how many steps it takes to get 9 cents, or how many different types of coinage you can create from 9 cents. So I'm done there. So I can cut off the tree there. And if you use this, you get an O of nm algorithm, which is obviously much better than this. But what's really fascinating is that if we use this technique of generating functions, which was talked about in an earlier lecture, we can actually arrive at a constant time solution, which is something you don't usually find in these kinds of problems. And it's really fascinating how you get there. So the main focus of this talk is really solving that problem. And in order to solve that problem, we have to step back and really motivate the idea of generating functions, because it's very easy to get confused about what these generating functions are supposed to do. And what I find is the most useful way of thinking about it is to go back to middle school algebra and recall the process of multiplying binomials using the FOIL method, right? So when you multiply 1 plus x times 1 plus x, you get 4 values. You get 1, you get x, you get another x, and you get x squared, right? What I want to do when I have this is model the polynomials as choices. And what I mean by that is, let's say 1 corresponds to the choice of staying still, and x corresponds to the choice of taking a step forward. And let's say you frame each of these multiplications, so each of these individual binomials, as like a binary choice. Either you stay or you step, and you stay or you step, right? And when you make this choice, this polynomial actually encodes the answer for you in a way, because it tells you that there's one way to take 0 steps, right? That's to stay and stay. There's 2 ways to take 1 step. That is to stay and step, or step and stay. And then there's 1 way to take 2 steps, which is to step and then step, right? And this might seem like almost like a childish exercise, but it really is telling you something powerful about what polynomials can do. And that is, you can kind of model the multiplication and addition of polynomials as choices. And this becomes even more relevant if you think about, a classic equation in probability and algebra, and that's the binomial theorem, which states that if you have, let's say, 1 plus x to the n, then that is equivalent to the sum of n choose k times x of k for where k goes from 1 to n. And if you think about it in terms of our previous problem, what this is telling you is that after n rounds of choices to step or stay, there are n choose k ways to have taken k steps. And so our idea of the choose function really maps onto this well. And ultimately, what we're getting at here is that polynomials can encode useful combinatorial information. And importantly, we should think about the addition of polynomials as an OR operation, where we're choosing between different possibilities, and the multiplication as a sort of and, right? And this will become even more visible when we think about this in terms of the change-making problem. So let's say instead of having this, infinitely many coins at our disposal, we start with 1 penny, 2 nickels, and a dime. Now, if we try to model this in the generating function sense, we can represent our problem as the multiplication of these 3 polynomials, right? And what this corresponds to is essentially 0 or 1 pennies. So this models the choice of pennies. This models the choice of nickels, right? We can choose 0 nickels, which corresponds to the x to the 0. So the exponent here is really representing the monetary value of the coin we're choosing. X to the 5th is 1 nickel, obviously, because a nickel is 5 cents, and 2 nickels corresponds to x to the 10th. And then you're also choosing between dimes, right? You can choose 0 dimes or 1 dime, right? And that might be a long-winded way of going about this, but what you do actually, when you multiply this polynomial out, is you get every answer you could possibly ask for in this problem. So for instance, this polynomial, which is just the result of multiplying these polynomials out, it encodes that there are 2 ways to get 11 cents. And the way we do that is we look through all of the different exponents, we see where x to the 11th is, and we look at its coefficient. And that coefficient told us there are 2 ways to multiply all these polynomials to get x to the 11th. And similarly, it tells us there are 2 ways to get x to the 10th. And that corresponds to either choosing 2 nickels or 1 dime, right? And it encodes a whole lot more information. It encodes everything, every single combination. And that is kind of the power of generating functions in the general sense, really. And the natural extension for our problem is that we actually have infinite pennies at our disposal. We have infinite nickels, we have infinite dimes, and of course, we would have further coins like quarters and half dollars and dollar coins. And really what this becomes is, instead of having a finite polynomial, we have an infinite one, right? And this becomes kind of an infinite sequence, really, if you think about it. And it becomes the question of how, and then really the question becomes, how many different ways can we represent k cents? So this question turns into finding the coefficient of x to the k after multiplying these polynomials out. Now, of course, these are infinite polynomials, so finding, x to the k is kind of hard. It's doable. You can kind of construct some algorithm where you're choosing, your top bounded, polynomials effectively, but there are other ways of going about it. But first, I just want to really step back and say this is generating functions at like its intuitive level. And if we zoom out, if we really think about, if you go to a textbook and you look at what a generating function is, like at its pure definition, the idea is that you take a sequence, an infinite sequence, and you plop it, and you smack it onto the coefficients of an infinite sum of polynomials, or it's an infinite polynomial, right? And when people introduce it with this definition first, I think there's often this confusion that comes about, which is, why am I attaching it to a polynomial? And well, the answer lay in our previous discussion, which is that the polynomial can help us encode information, and it can help us do combinatorial operations. I like this quote about generating functions, which, I mean, you'll see on the Wikipedia page, but it's by George Polya in Mathematics and Plausible Reasoning. And he states that a generating function is a device somewhat similar to a bag. Instead of carrying many little objects detachedly, which could be embarrassing, we put them all in a bag, and then we only have one object to carry, the bag. And I think, when you go about doing the math, which we're going to do a little bit of in solving this problem, you kind of get a feeling for what he really means by that. The generating function is an elegant way of encoding all our information, really. So if we go back to our problem, right, we can construct the generating function. We're interested in the generating function of all of these possible choices of coins, right? The choice of pennies, the choice of dimes, the choice of nickels, the choice of nickels, the choice of dimes, the choice of quarters, and etc. And really that comes down to multiplying all of these infinite polynomials. Now, nicely, we can use this trick. I mean, it's not really a trick. It's a pretty well-known mathematical identity about geometric series, which allows us to actually turn this function into a closed form expression, right? So we can take this and make it 1 over 1 minus x. We can take this and make it 1 over 1 minus x to the 5th, and so on for each coin denomination value. And this might seem like it's masking the use of generating functions, right? Because wasn't the whole purpose that we wanted the coefficient? And the truth is, yes, we do want it. And we can still get this coefficient by using techniques of calculating the Maclaurin series, which would involve taking derivatives And essentially, like this polynomial or this rational expression alone is enough to get us an answer in O of nm runtime, if you really think about what you're doing when you're taking the derivatives. And that is one way of getting the answer. Well, of course, what we're curious in is a constant time solution, which I will get to. But I really want to stop and emphasize that this expression, the whole point of this expression, again, was that if we express it as a polynomial, as an infinite polynomial, the coefficients will give us the answer to our question. So for instance, if we're interested in how many ways can we express k-sense, then we go to the coefficient of x to the k in our infinite polynomial expression, and that coefficient is our answer. So I just want to make that very clear, and I want to emphasize that because that's an important point that should not get lost here. So in order to create a constant time solution, we take advantage of the specific series of coinage that we're using. And that's, so for instance, we define this variable, this function called b of x, which is, it's very similar to what we had before, with a few minor differences. And, you know, coming up with b of x is perhaps not an easy feat. This is one of those moments in math where it's like, okay, that step was not very visible, perhaps, but it's a step we can take. And what this step does, it allows us to do, is write a of x in this expression, where we have this finite polynomial times b of x to the fifth. And if we actually expand this out and we consider the different like exponents, how the exponents will be affected when we take the series version of this, we find that the coefficient of b of k is equal to a of 5k, and it's equal to a of 5k plus 1, and 5k plus 2, and 5k plus 3, and 5k plus 4. Now, this might seem kind of weird to you at first, like, how are all of these a values equal? But really, if you plug in like k equals 1, this should really make sense, right? There's this, okay, you have two ways to express 5 cents, right? You can either express it all in terms of pennies or in terms of 1 nickel. In terms of 6 cents, it's still two ways, right? You can either do all pennies or you can do penny and nickel, right? And you see that, like, when you're within this range of 5 values, the way our coinage system works is that really the pennies fill in for you, and they fill in such a way that all of these values are the same. And b of k is recording that. So b of k, in a sense, is kind of, so the b polynomial is kind of squishing down our a of x into something simpler, where we don't have as much repetition. It's kind of squeezing out the redundancy in a. And just to emphasize again, an is our answer. So it suffices to know b of n, right? Because if we just start with a of n and we take the floor of n over 5 and put that as our b, the k value for b that we're expecting, then we can look at b. So really, now that in order to find a of n, we can look at bn, and where bn is the polynomial coefficient, the nth polynomial coefficient for b's infinite polynomial expression. It's Maclaurin series, so to speak. Now, this is where another strange but interesting step of algebra comes in, and that's that we can write b of x as yet another polynomial divided by a different polynomial. And we're going to talk about what c is. Okay, in fact, I could show you on this next slide. C is a polynomial that is 81. So it's 82 different values. So actually, I wrote this wrong. This should be 81. So it's a very long polynomial. It's not something you would come up with immediately. But I'm trying to think of things in terms of their purpose in terms of solving this problem. And when you step back, the whole point of putting c of x here was that it allows us to simplify b. And what I mean by that is c of x is a finite polynomial. It might be disgusting, but it's finite. And then we have this expression on the bottom. We have c of x divided by 1 minus x to the 6th to the 20th. And it turns out that this might be, another seemingly unnatural step to take, but we have an expression for this in terms of another finite polynomial, right? So 1 over 1 minus x to the n is equal to this expression. It's kind of similar to the binomial theorem in a way, but it's you have an inverse here, and that's why the choose function kind of changes a little bit. But what's important is that now we have a finite polynomial times a polynomial that grows in terms of n, right? Because this 1 minus x to the n will actually vary. And okay, so what's important here is that when we consider that C is a finite polynomial, then we could write b of x as the product of these two polynomials. So again, this should be 81. And if we zoom out again, what we want is a of n. It suffices to find b of n. So if we actually consider, when we multiply these two polynomials out, we want to know what is the j and the k such that, because we have, this is like how we're indexing these polynomials, and then this in k is how we're indexing these. We're interested in j and k such that j plus 20k equals n. And the reason that makes sense is because we're interested in all the ways that we can add up different combinations of these two to add up to something of x to the n order, right? And the way we do that is if this j and this 20k add up to n, essentially. And there can be multiple ways of doing that. But what's interesting, and this is something that if you read the textbook, they're not going to explain to you explicitly. It took me a while of kind of banging my head against this to understand. It's that if you look at this expression, if you really look at it, what it's telling you in terms of at least modular arithmetic is that n is congruent to j mod 20. And what's important to note is that j ranges from 0 to 81, right? So j has a finite range here. So if n is congruent to j mod 20, that means there's finitely many values of j that we can choose from. And if that's the case, that means there's also finitely many values of k we can choose from, right? Because, and that means that essentially, whenever we're trying to find the first value for, or like the coefficient value of, which is bn, we can look at essentially a finite number of terms, and specifically at most 5 terms, because there's at most only like 5 different distinct n which can fit in j mod 20. Okay, so since j only ranges in this way, there's only finitely many n that could fit, that we can choose. So finitely many j we can choose from, and then finitely many k, and then that means that we can find n essentially in a always finitely many, a finite amount of operations, essentially. Which means that the solution n is a sum of at most 5 terms, which is exactly what we want if we're actually trying to think about this in terms of a constant time algorithm, right? So there is an example in the textbook that I could look at. In fact, I think I'll just do that quickly. Okay, so for example, if we are interested in a of 1000, then we can look at b of 200, right? Because the whole idea was that b was immediately determined by a, and b was like squishing down a by a factor of 5, right? And then b of 200 essentially is, we look at all of the different values of c that were congruent to 200 mod 20. And that is essentially C0, C20, C40, C60, and C80, right? And then because we know that, we also can determine immediately, once we have j, we can immediately determine k. So then we know exactly what this coefficient will be, the k plus 5 choose 5. So then this essentially, it always boils down to a sum of at most 5 terms. And in this case, you get over 2 million as just like an answer, right? So that is the finite time solution. And it might not immediately click what's happening there. But if you look over multiple times, perhaps, or just like let it sink in, it kind of comes to you. And then it's like, wow, that's pretty cool what just happened. We just use this weird mathematical technique to arrive at a constant time solution to what seems to be a pretty hard combinatorial problem. And what's interesting is that, and this is what motivates the kind of broader mathematical discussion here, is that if we had a really wacky kind of coinage, where we had, for instance, a 1 cent coin, like a penny, but also a 2 cent coin, and a 3 cent coin, and a 4 cent coin, and a 5 cent coin, and a 6 cent coin, and so on, then this generating function becomes like, essentially, we're multiplying 1 over 1 minus x to the k for all k, right? If we go back, remember, we were just multiplying for all the relevant coinage values, like 1 minus x, this was pennies, this was nickels, dimes, quarters, and etc. But then if we abstract this, then what we're really working with is like an infinite kind of product of these. And you can look at the math here and you could say, okay, well, this function, if you go into the annals of mathematics, this function is equivalent to something called the partition generating function. And then we could go into talk about partitions. And that's what we're going to do. But it's also, as we talk about partitions, I want us to think about how this sort of change making that we're doing here is very much equivalent to the abstract idea of partitioning itself. And I hope you get a sense of that as we talk about partitions in the more rigorous mathematical sense. So let's define what a partition is. I kind of regret putting the rigorous definition before the intuitive one. The intuitive one here is, how many ways can I arrange n objects into k distinct piles? And I like the example that they give in the textbook. It's like, if you have 10 poker chips, how many different ways can you arrange those poker chips into little piles to, make your enemy scared? The way I tried to formulate it mathematically was, it's a little opaque at first. It's a partition of some positive integer n is a k tuple of positive integers, and that k tuple, that could be, since it's positive integers that you're adding up, ultimately the k has to be less than or equal to n. But it's a k tuple arranged in descending order, and this order is just so that we can like distinguish between the different partitions easily. And it's arranged, and essentially these a add up to n. So every value in this little bucket adds up to n. And you can think about it where each entry actually represents the size of a different pile, right? So if you have if you want to express like 3, right? You're trying to partition 3 objects, you can perhaps partition in, like, you can take one pile of one object and another pile of 2 objects, and then that would be expressed as 2, 1, because it's in descending order. And we have the fact that 2 plus 1 is 3. So, okay, so we can think about this in terms of specific sets of size k. So for example, the number of ways we can distinguish n objects into k piles is denoted by p of n comma k, right? Because there are kind of two things at play: the total number of objects and the total number of piles that we're splitting it into. This is an illustration of the example that they gave in the textbook for the 15 ways to stack 7 poker chips. So obviously you can just take your 7 chips and stack them in one stack. And this is the tuple representation of that. You can take 6 and then 1. So that's 2 piles. So if you think about p of 7, 2, there are 3 different ways of doing that, right? You can either do 6, 1, 5, 2, and 4, 3. And note that if we try to do 3, 4, that's not really allowed because of the way we structure this, right? We said it has to be in descending order, right? And then in terms of 3 piles, we have 5, 1, 1, we have 4, 2, 1, we have 3, 2, 2, and we have 3, 3, 1. So again, note that they're all descending order. And then if you look at this graph, at this diagram, you should be able to immediately recognize that p of 7, 3 is 4, because there are 4 different ways of arranging 7 poker chips in 3 piles. And so on for 4, and for 5, and for 6, and then 7. Another way, so there's kind of the usual way of visualizing a specific partition is using something called a Young diagram, where you start with, I guess in this case, it's 14, 16, 17 different. So 17 is your n, right? You have 17 objects, and you're considering how many different, ways can I arrange 7 objects? Oh, so 17 objects into k piles. In this case, it would be 5 piles. So this is one specific partition, right? And this partition is represented by the fact that there are 6 in the first pile, 4 in the second pile, 4 in the third pile, 2 in the fourth pile, and 1 in the fifth pile. And then this is not something we'll really talk about too much because it won't really, but it's something that's useful in the proofs of some of the topics that we're going to discuss. And it's this idea of a partition of the conjugate of a partition. Sorry. And geometrically, that just means that you take your Young's diagram and you flip it along like the diagonal, the obvious diagonal. And obviously, I mean, that results in a very different partition. In fact, it's a different length partition. Instead of being 5 long, now it's 6 long, right? And this is useful because there are certain properties that partitions and their conjugates have. For instance, like there's only very specific cases where a partition can equal its conjugate. There are the conjugate is unique. Like if a partition can't have like 2 different conjugates. And these are just useful kind of mathematical properties for it to have, really. I realize maybe I should stop if there are any questions about the idea of partitions. Probably should have also stopped in the generating functions category, but otherwise I'll just go on. But you can feel free to interrupt me, of course. We're almost done anyway. So the partition function, which is different from the partition generating function, which I will go back to, is essentially just adding up the different kinds of partitions you can make. So for example, you add up the different ways you can partition n objects into 1 pile, and then you add up that with the number of ways you can partition n objects into 2 piles and 3 piles, and so on up to n. And the idea is that this Pn essentially just represents all the different ways you can split n objects into different distinct piles. And this is kind of the thing we're most interested in here. So the first few values of this partition function, you can visualize below. It doesn't grow terribly fast. But it's particularly hard to actually find a closed form expression for Pn. And that's kind of where the mathematical quest really begins with this subject, is trying to find out ways to express the partition function. And what I mean by closed form, of course, is like something that's not recursive. It's something that's not dependent on like lower forms of the partition, but like I can give you an example of, I'm going to give you an example of a partition function, of a way of like calculating the partition function for some n that is not closed form, that it's explicitly recursive. We're going to walk through this kind of slowly because it might be kind of hard to grasp at first. So if you're given any partition of n and you denote it as, and it's some k partition, right? So it's a1 ... ak, right? For instance, if I had 3, I can have 2, 1, right? A very simple partition. Now, we can consider 2 different cases on this partition. We can say, okay, AK could be 1. Like the last value of this could be 1. And in that case, what we do is we can say, well, A1 to AK minus 1 is a partition of n minus 1. Because, and I think this might be useful with like, if I write this out, is there a way for me to draw, Zach?
I'm not sure how to do it without like exiting the screen share.
Maybe I could just draw here. Wait, let me try this. Okay, so for example, if I have a partition, let's say 3, this is 2 and 1. This is a partition of 6, right? I have 3 in one pile, I have 2 in one pile, and I have 1 in another pile. I'm saying if a of k is 1, so this last value is 1, then we can essentially chop it off. We could say 3, 2 is a partition of 5, right? So 5 can be split into this. And this should seem like a pretty simple thing if you look at the concrete example and even in the abstract. What's important is that we can do this for any partition that ends with 1. And the number of partitions that end with 1, and since we can create all partitions of n-1 using this formula, assuming we have all of the partitions of n, then what this allows us to do is essentially say that the number of partitions of n that end with ak as 1 is pn-1 k-1. So, I mean, we can walk more through this specific example. For instance, 6 can be like this partition. It could also be, well, actually, is that the only one that ends with 1? I'm trying to think. Oh, wait, no, it could also be 3, 1, 1, 1, 1, right? So this is another candidate for one that we can convert into a partition of 5. We can also do the 2 and then a bunch of 1, ... It's going to be too many ones for me to write my poor little finger. This one is also one we could chop off the 1 and then make this a partition of 5. The point is that we can do this for any partition of 6 that ends with 1, and it'll always become a partition of 5 that it could end with 1. Like in this case, it does end with 1 if we cut this out. But what's important is that this generates all of them. So this accounts for one sector of the partitions we have. Now, in the other case, if ak is not equal to 1, then we can do something where we subtract 1 from every single element in the partition. And then that becomes a partition of n-k. So again, it's useful to look at a specific example. If we have 6 expressed as a partition, let's say 3, 3, then if we apply this method, it allows us to create, sorry for the really long line, it becomes 2, 2 if we subtract 1 from every single element of the partition. And this is a partition of 4. And again, the beauty of this is that every partition of n-k can into k elements can be found in this way, assuming that we have all the partitions of n. And that allows us to equate this other sector of the partitions of 6 or partitions of n, and we can quantify it as this. So what that allows us to do is say, okay, well, there were only 2 sectors, right? It could either end with 1 or it doesn't end with 1. So this covers all of our bases, right? So then that means that p of n comma k is either going to be the sector that ends with 1, and therefore there are this many of them, or it's the sector that doesn't end with 1, and there's this many of them. And we simply add these 2 together. And this gives us a beautiful recursive formula for p of n comma k. And as you might realize, you can use this to then generate p of n, right? Because we know that p of n is the sum of p n minus k, or of p n k over k. Oh, this is not the best marker, right? It's because we sum away the k's. So if we use this applied in here, we have a recursive formula for p of n, right? This got kind of messy, but that is kind of the first step when understanding how you want to express partitions. Now, if we go to the next slide, this might seem like it's coming out of nowhere and slapping you in the face. I want to step back and remember that the generating function for the partition And again, that's different from the partition itself. So, okay, so eventually, okay, we remember that the whole point of the generating function for the partition or for any, so the partition function, of course, is a sequence, right? So we want the partition generating function to be of the form P0 plus P1 of X plus ... right? And I mean, I guess I should just draw this other one, P2 to the X squared, right? And then the whole point is that if, okay, let's say we want the partition function for n equals 2 or n equals 17, then we look at P17. We look at the coefficient of X to the 17, right? And as we might recall from the end of our generating function section, the partition function, the partition generating function is represented by the infinite product of, of 1 over 1 minus x to the k over all k. And this is kind of, you can think about this very similarly to the whole coin problem, because essentially what we're doing when we're creating a partition is essentially, we can think of this like we have like different kinds of coinage, essentially. Like this could be represented as the coin vector that we're using. And then the number of different piles is the number of, is like the number for each coin. But I don't really think we have time to reinforce that too much. The idea here is that there's this function called the Euler function, which is the inverse of the partition generating function. So instead of having 1 over 1 minus x to the k, we just have 1 minus x to the k. And we have the infinite product of that up to infinity. This function happens to be equal to this interesting alternating sum of the pentagonal numbers, of powers of the pentagonal numbers, which again might seem out of nowhere. You can just think of the pentagonal numbers as an interesting sort of sequence of this form, right? And you see that, and then this is like what the sequence is. Why is this useful for our discussion of partitions? Well, it implies through some steps that I don't really have time to get into, that you can create a different sort of recursive function for calculating the partition, and it's of this form, and it's a faster and it's, okay. So what happens is that you these are all what is it, pentagonal numbers, right? And so the pentagonal numbers grow quite a bit faster than, like, say, your normal integers, right? So you take this sum over this alternating, not quite alternating, sum of p of n minus different pentagonal numbers. And since pentagonal numbers grow kind of fast, then this gives you a better recursive formula for the partition function, right? And again, if we want to stress the importance of generating functions, I will note that this method of finding this particular recursive function comes from our generating function. And so yeah, again, generating functions can help us solve problems. Now there's one more result that I want to go through that's obviously way too complicated for this discussion, or for any kind of rigorous mathematical treatment. But it's really fascinating, and that's that if you take the partition function to extremely large values of n, you find that it converges to a function that includes e to some power of pi with some square roots that have n in them. And this asymptotic formula was obtained by G.H. Hardy and Ramanujan in 1918. These are like pretty famous mathematicians. This kind of comes from a more like complicated expression that could be simplified. What I want to stress here is that this partition function, which came out of a very kind of direct combinatorial problem, it converges towards this expression that has, these values that we usually associate with like analysis. We associate with like circles or like exponential functions. And I'm gonna delete those two. And it's one of those weird moments where combinatorics seems like it actually is starting to touch on other things and like more continuous kinds of topics, which is something that, generating functions help us get to. But it's also just something you see in this result purely. And I think that's kind of how I want to end this talk, by kind of looking at the ocean of mathematics and such strange results as this, and just looking at in awe at like the connections that you can make with starting with simple problems like changing coins. So yeah, thank you for listening, and I welcome any questions.